Geographic Information System, Lesson 12, Data Quality Issues. In previous chapter, we have discussed about the different data display method. In that, we discussed about different map representation, types of qualitative maps, quantitative maps, map design, map output. In this chapter, we will understand about different data quality issues that occur during the usage of GIS software or during the data entry point into the GIS system. Objectives. The main objective of this chapter is to discuss about the different data quality issues that are involved in handling the spatial data so that it is precise, rapid and sophisticated. The chapter can be divided into components of data quality, accuracy, precision and resolution, consistency and completeness. Error in accuracy and imprecision in spatial and non-spatial data are the problems caused due to the little attention paid by the remote sensing and GIS user community. Though there is an awareness that all the data suffers from inaccuracy and imprecision, but their effects on GIS problems and solution are not considered in great detail. The scenario has changed substantially in recent years as quality of the output is an important component for any mapping activity. It is now considered that a GIS project can make or break due to the error. Inaccuracy and imprecision can create a lot of problems, can change or alter the data. As a result, the final output is not showing proper results in the GIS project. The usage of error in the GIS system is including the statistical concept of error, that is variation in the data structure. Therefore, the data quality check has become very important component of any GIS project. The meaning of the quality depends upon the context in which it is applied. The term is commonly used to indicate the superiority of manufactured items or at least to the high degree of craftsmanship or artistry. Quality is very difficult to explain or define for a data, as data it does not contain any physical characteristics that can allow the quality to be easily accessed. Quality is an intangible property that is completeness and consistency. More commonly, data quality refers to the accuracy and precision of a particular database used in a given application. Thus, quality of a data has become a concern among the user community for different reasons, like there is large amount of data production is given by private sector. The use of GIS in decision support tool has increased in the present scenario as it supports in real-time problem solving mechanism. There is a large increase of reliance on the secondary data sources. These trends have contributed to reappraisal of the responsibility of the data producer and consumer for the data quality. Responsibility for accessing whether a database meets the needs of a particular application has therefore shifted to the consumer, who is in a position to make such an assessment. This is referred to as determining fitness for use. From the perspective of the data producer, quality refers to the difference between the actual characteristics of the product and the relevant specification that it defines. Information on quality is immensely useful in managing the production process, particularly if the results of the quality analysis point back to the suspect source of the data. Peter Fisher in 1999 discusses alternative models for uncertainty. The traditional scientific concept of measurement error, which accounts for differences between observer or measuring instruments, turns out to be far too simple as a framework for understanding quality in geographical data. If agreement can be reached on how to measure and express data quality, then this information should be made available to the users preferably by storing it as a part of it or in conjunction with the database. With adequate information available on data quality, it is possible to determine its effect on the results of GIS analysis and to reflect on the uncertainties present in the database relating to the decisions made with GIS. Components of data quality. Then the location is being observed and mapped. The location can be described with spatial component, temporal and thematic component. Space is an important component in defining a geographical location and it is a dominant component for data quality. Although poorly accommodated in conventional geospatial data models, time is crucial for an understanding of geographical phenomena, not as entities that exist at the same location, but as events that appear and disappear in the space and time. The space component of a given location with respect to time is applicable only for that period of time, and the space component of that location may vary with the time compared to the past. The second problem is that geographical phenomena are not really about space but about themselves. For example, when a state boundaries are marked on the map for India, it is seen change in joining the states and division of states across the time. Thus, it is important about the state boundaries rather than the space and time concept. Data quality components are the key elements to explain the accuracy and precision of data and the results of the data analysis. Data quality components can be differentiated in space, time and theme. There are several components of quality, namely accuracy, precision, resolution, consistency and completeness. These terms are used at most interchangeably with reference to spatial data, but we will need to establish more exact definitions. Accuracy is the degree to which information on a map or in digital database matches true or accepted values. For example, how the road network is being mapped in a digital format when compared to a true road network on the ground. Accuracy is an issue pertaining to the quality of data and the number of errors present in the data set or map. There are two accuracies, that is horizontal and vertical axis accuracies, are considered while discussing about a GIS database with respect to geographic position as well as attribute, conceptual and logical accuracy. In a GIS database, the level of measurement in exactness of description is referred to as precision. Precision means how exactly the map data is present in the database when compared to the real value data. In the precise location, data may measure a position to a fraction of a unit. The precision attribute information may specify the characteristics of features in great deal. Surveyors may make mistakes or data may be entered in database incorrectly. The level of precision required for a particular application varies greatly. For example, engineering projects such as roads and utility construction require very precise information, measures to millimeter or tenth of an inch. High precision does not indicate high accuracy, nor does high accuracy imply high precision. For example, a map data may be having a high precision, that is extremely small value is being represented in the digital format, but it may lack the accuracy, that is relationship between the map data with the ground data. But high accuracy and high precision are both expensive. GIS practitioners are not always consistent in the use of these terms. The resolution of the data set defines the smallest object of the feature that is included discriminably in the data. Scale and resolution are intimately related because there is a low limit to the size of an object that can be useful shown on a paper map. This limit is often assumed to be 0.45 millimeter as a rule of thumb. So, the effective resolution of a map is 1:2000 is about 1000 into 0.5 meters or 50 centimeters. The standard of most mapping agencies are common map skills, assuming 0. Consistency refers for the absence of paper and contradiction in a database. Completeness refers to relationship between the object in the database and abstract universe of all the objects. Accuracy. Accuracy can be started at the point of entry attribute value model, which serves as conceptual basis for most database implementation of real world phenomena. According to this model, entities represent real world phenomena such as roads, streets, districts, cities and hazardous waste sites, and attributes specify the relevant properties of these objects such as the width, the number of lanes, while values give the specific quality and quantitative measures pertaining to a particular attribute. For example, when a road is taken into consideration, the name, the road, is considered as entity, earth and the length of the road is considered as attribute, whereas what type of road it is present is considered as value. In this model, error is defined as discrepancy between the encoded and actual value of the particular attribute for a given entity. Accuracy is their inverse of error. This model can be used to define spatial component, temporal and thematic error for a particular entity as the discrepancies in the encoded spatial component, temporal and thematic attribute values. The geospatial data always require a model that specifies common implicitly or explicitly the required level of abstraction and generalization related to the real world phenomena, and accuracy fits for this definition. Accuracy is a relative measure rather than an absolute one, since it depends upon the intended form and the content of the database. Different specification can exist for some general types of geospatial data. Accuracy of the GIS data can be discussed in the terms of spatial accuracy, temporal accuracy, thematic attribute data accuracy, conceptual accuracy. Spatial accuracy. The accuracy of the spatial component of the database is called spatial accuracy. It is also called positional accuracy, as the accuracy depends upon the position in the database. Accuracy and precision are the functions of a scale. This means that when we see a point on a map, we have its probable location within a certain area. This applies to the lines also to make us beware of the dangers of false accuracy and false precision. That is, reading location information from map to levels of accuracy and precision beyond which they are created. Accuracy and precision are tied to the original map scale and do not change even if the user zooms in or zooms out. 4-point error is defined as the distance between the encoded location and the location as defined in the specification. Errors can be measured in any one of or in combination of 3-dimensional of space. The common measures are the horizontal measures, that is distance measured in x and y coordinates simultaneously, and vertical error, that is distance measured in set coordinates. Various metrics have been developed to summarize spatial error for set of points. Horizontal error is a 2-dimensional extension of the classical error model, in which error position is defined in terms of a bell-shaped probability surface. Error in the lines arise from these errors in the point that define those lines. Error is usually defined for lines using some variant of the epsilon band. The epsilon band is defined as the zone of uncertainty around an encoded line within which there is a certain probability of observing the actual line. The epsilon may be interpreted as if zone as a uniform sausage indicates the distribution of error is uniform. Temporal accuracy. Temporal accuracy is nothing but the relationship between encoded and actual temporal coordinates. Assessment of temporal accuracy depends upon the ability to measure time objectively using a standard temporal coordinate system. Another impediment to the measurement of temporal accuracy is that time is often not dealt with explicitly in geospatial database. Temporal information is often omitted, accepted in database designed for explicitly historical purposes. Attribute accuracy. The non-spatial data linked to location may also be inaccurate or imprecise. Inaccuracy may result from mistakes of many sorts of non-spatial data can also vary greatly in precision. Precise attribute information describes phenomena in great detail. For example, a precision description of a person living at a particular address might include gender, age, income, occupation, level of education and many other characteristics, and imprecise description might include just income or just gender. Thus, attribute accuracy gives lot of information in a given data. Conceptual accuracy. Large amount of GIS data depends on abstraction and classification of real world phenomena. The users determine what amount of information is used and how it is classified into appropriate categories. Some things users may use inappropriate categories of misclassified information. For example, when the city relation size is considered as a class, it is ineffective way of representing the literacy rate. The inadequacy of classification power will limit the effectiveness of a GIS designed to manage. Even if the classification categories are employed, data may be misclassified. For example, when a drainage system is being considered, it involves classification of streams and rivers by order, that is, where a particular drainage channel fits within an overall tributary network. Individual channels may be misclassified distributaries or miscounted. Yet, some studies might not require such a position categorization of tree model at all. All they may need is a location in the name of wall streams and river of order. Precision and resolution. The amount of detail that is used is known as precision. It is also known as granularity or resolution. Resolution is commonly used in GIS and related fields and adopted here to avoid confusion with the mathematical concept of precision. Resolution is also limited because geospatial databases are intentionally generalized. The generalization include elimination and merging of entities, reduced production in detail, smoothing, thinning and aggregation of classes. Generalization is inevitable because geospatial database can encompass only a fraction of attributes and their relationship that exist in real world. When a particular application is taken, then the degree at which the database is used depends upon the resolution. The resolution for a database should match the requirement of the application. Resolution is also important because it plays a major role in interpreting accuracy. And we can discuss under the concept of spatial resolution, thematic resolution and temporal resolution. Spatial resolution. Spatial resolution is nothing but the dimensions of ground object or pixels making up an digital image. This spatial resolution is very much important in the field of remote sensing data. This concept is applicable without modification of raster database. For vector data, the smallest feature that can be used to determine in terms of rules for minimum mapping unit size, which depends upon map scale. The spatial resolution refers to the fineness of the detail that can be preserved, while the sampling rate defines the ability to resolve patterns over space. For remotely sensed data, resolution refers to the pixel size and resampling and sampling rate to the space between pixels. Thus, in theory, one could mix high spatial resolution with low sampling rate or low spatial resolution with high sampling rate. Normally, resolution and sampling rate are approximately equal. Temporal resolution. Temporal resolution is used for the minimum duration of an event that is discernible. This temporal resolution basically depends upon the recording interval and the rate of change in the event. The shorter recording interval needs to higher temporal resolution, common just ask faster film as given. The ability to photograph quickly moving objects. For geospatial data, the situation is more complicated because interaction between spatial and thematic resolution must also considered. Thematic resolution. The mapping of thematic resolution depends upon the measurement scale. For quantitative data, resolution is determined by the precision of the measurement device. For categorical data, resolution is defined in terms of the fitness of category definition. Land cover classification system define the level of detail in taxonomic definition in terms of the spatial resolving power of the remote sensing system. Consistency refers to the absence of apparent contradiction in the database. For geospatial data, the term is used primarily to specify conformance with certain topological rules. These rules vary with dimensionally. For example, only one point may exist at a given location. Lines must intersect at nodes, and polygons are bounded by lines. Elimination of topological inconsistency is usually prerequisite for GIS processing, such that most database of topological cleaned before being released. Topological consistency is one of the aspects of consistency in the spatial domain. Spatial inconsistency can also be identified through redundancy in spatial attributes. Non-redundancy implies that there is independence between two attributes such that meaningful consistency contains do not exist. In the thematic domain, the ability to identify inconsistency required a level of redundancy in the thematic attributes. For example, the three socio-demographic variables population, mean household size and total number of households. Of course, the identification of an inconsistency does not necessarily imply that it can be corrected or that is possible to identify which attribute is in error. Thus, inconsistency is approximately viewed as a measure of internal validity. Completeness. The relationship between the object in database and the abstract universe of all such objects is considered as completeness. Selection criteria comment definition, another mapping rule used to create the database, or important determinants of completeness. The abstract universe can be defined in terms of desired degree of abstraction and generalization. There are different types of completeness. They are feature or entity completeness, attribute completeness, and value completeness. The feature or entity completeness can be defined over space, common time, or theme like a database that depicted common the location of historical monuments in the state of Andhra Pradesh placed on Register of Department of Tourism Department in 1987. This database would be incomplete if it only included buildings where in the Hyderabad district. This may be said that database incompleteness in space, since Hyderabad district covers only a portion of Andhra Pradesh. if all the buildings placed in the register by 1990 is said to be incomplete in time, since historical monuments have been added after 1990. If the database consists only monuments of buildings, then the incompleteness in theme is due to the omission of other types of historical monuments. Feature or entity completeness may be explained by means of data completeness and model completeness. Data completeness is used to access data quality which is application independent. Model completeness refers to the agreement between the database specification and abstract universe that is required for a particular database application. Model completeness is application dependent and therefore has aspects of fitness for use. It is also a component of semantic accuracy. The second type of completeness is attribute completeness. This can be identified as the degree of which all relevant attributes of a feature have been included. Final type of completeness is value completeness, which refers to the degree of which values are present for all attributes. Summary. In this chapter, we understood how the data quality is depending upon the different aspects in GIS. For example, the quality of data is depending upon the accuracy, which can be divided into spatial accuracy, temporal accuracy, attribute accuracy and conceptual accuracy. The quality of the data depends upon what type of resolution is being present in the database, which is again suitable for a specific application. This resolution can be divided into different types like spatial resolution, temporal resolution, thematic resolution. The data that is present in the database should have a consistency with the real world phenomena. And last, completeness, which is the relationship between the object in the database and the abstract universe of all objects.